All right, so we're going to finish up this week looking at section 5.4. Okay, part 1, we'll split this into 2 sections. 5.5 will be our last section on logarithms, and then after that we'll start chapter 6, which gets into trig. So a log function, it's the inverse of an exponential function. Okay, so what that means is they're opposites. So if you want to think of another pair of functions that are inverses, think of squaring and square rooting. Okay, one of them is the opposite of the other. So if exponential functions increase, like an exponential growth function, it increases extremely quickly. What do you think is going to happen with a logarithmic function? It's going to increase very slowly. Okay, very, very slowly. In fact, if you take a log of a number even in like the hundreds of thousands, the y value might only be like 6. All right, so if you let the x value get really, really huge in a log function, okay, like let's take the log of 100,000. I'm sorry, 5. So the y value would only be at 5. All right, so that's going up very, 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 very slowly. Okay. And inverse functions are mirror images of each other, not over the axes, but over the line y equals x. Okay, so what I have in blue is a exponential. What I have in red is a log. And that black line is the line y equals x. Okay, y equals x has a y-intercept of 0 and a slope of 1. So it cuts right through the first and third quadrants on a 45-degree angle. And if you were to take the graph in blue and flip it over that black line, you would get the graph in red. Okay, so what that shows is that they are inverse functions. Anytime a function is a mirror image over that black line, that's an inverse function. Okay, any questions on that? That those are mirror images?
Okay, so which one is the logarithm?
The logarithm is the blue one. I'm sorry, the logarithm is the red one. Because it's going up, but it's going up very, very slowly. And the blue is the exponential because it goes up very quickly. Okay, any questions on that? All right. So when we write logarithms, okay, that's generally how you write it. And if you were writing this on lined paper, it would look something like that. Y equals log base A of x. That's how you pronounce it. So the x is not it's not an exponent. Okay, the x and the word log are right on the line. It's the A that's a little bit below. If you had an exponent, it would look like this. It would be up higher than the x. Right, so you pronounce it y equals log base A of x. Okay, and x is called the argument. Okay, in general, an argument is just the thing you plug into a function. So if I had something like this, I would say x minus 2 is the argument to the square root function. It's the thing I'm square rooting. When we start to study trig functions, I would say 4x plus 6 is the argument to the sine function. It's the thing that I'm taking the sine of. Okay? So it's just the thing you plug in. Now there's 2 logarithms that have special bases. Okay, well they have special names because of the base. And we have 2 buttons on the calculator for these special ones I'm about to talk about. Okay, if you have what's called a base 10 log, right? So if you plug in 10 for the A, that has a special name. Does anybody know what the name of a base 10 log is? Well, since it's the one that you use most of the time, okay, the one that occurs most often, it's called the common log. So if they ask you in a problem to find the common log of a number, that means they want you to take the log and let the base be 10. Okay, and there's a button on the calculator for this. Okay, so if you wanted to find the common log of something, I'll show you in a second how you do it on the calculator. Now, a lot of times when a number is used a lot, okay, or something it's understood to be there, like in this case, I didn't put a number in front of the x, but there's something that's here, even though it's invisible. Okay, it's a 1. Well, when we do common log, because it's used so much, you don't have to write the base. Okay, so if you ever just see the word log and there is no base written, you always assume that it's the common log. Okay, base 10. And that's how your calculator does it as well. All right, so if I go on the calculator and let's say I want to take the log of 13. Yeah, all I have to do is press the log button, okay, right next to the 7, 13. And the log of 13 is 1.14, or 1.114. Now, at this point, we have no idea what 1.114 means, okay? But we'll learn what that number actually is in a little bit. Okay, so that's one of two logs that have a special name. So common log, and the other log is right below it. Okay, there's another button for it, and the letters they use on the calculator might give you a hint at the abbreviation. Does anybody know what this log is called? It's an ln.
Something close to natural log.
Yeah, that stands for natural log. I know, why isn't it NL? I don't know. But it's written as ln.
Yeah, you know the LDP calculation works.
And that's called the natural log.
Can you go back?
Okay, and notice, what's the base on the natural log? E. When did we talk about E? When did that come up? Yesterday, right? When we talked about that special function, I graphed 1 plus 1 over x.
It's the base, right?
Yep.
The natural log.
Yep, that's the base of the natural log, E. Okay, and E is the number 2.718. It's irrational, so I know if you look at it on the calculator, it looks like there's a pattern to it, but the pattern, it doesn't keep repeating. It doesn't keep going 1828, 1828, 1828. Okay, it changes after that. Okay, so if you have a base of E, okay, that's called your natural log function. And just like with common log, because that one is also used somewhat frequently, there's an abbreviation for it. And the abbreviation is the button I showed you on the calculator, LN. Okay, so most of the time, either on a test or in a book, you'll never see log base E written. You'll always see the abbreviation for it, LN. So if I asked you to find the answer to this versus finding the answer to this, it's the same thing. Log base E of 18, find the ln of 18, no difference. These are the only two logs that have special names. If you have a base other than 10 or E, we don't have a special name for it. We just call it log base 3 or a log with a base of 8, okay, whatever the base is. Okay, but the other thing is we also don't have a button for it on the calculator. Okay, if you want to do a base 10 log, you press that button. If you want to do a base E log, press that button. If you want to do something other than those two, we have to figure out a way to type it in. Okay, there is a way to do it, but Not something we're going to look at today. Okay, so any questions on that abbreviation? All right, so the only thing you got to be careful with the abbreviation is you can forget what the base is, because when you write the abbreviation, the base is hidden. Right? Just like with the word log, if you just write log, the base is hidden. So you just got to remember that in this case, the base is an e. All right. All right, so when I graphed the log function earlier, okay, that was the one, I think it was in red. Let me just go back to it for a sec.
Yeah, it was.
Okay. The domain, you can see that it does head to the right forever, but does it look like it's heading to the left forever?
Approaching 0.
Yeah, on the x-axis it's
Yeah.
approaching 0, but we can't even use 0. Okay, so the domain is any number from 0 to infinity. Okay, that means you can take the log of any positive number. You cannot take the log of a negative, unless you want to get into imaginaries. Okay? So negative logs would give you a non-real answer. And that goes for the base and the argument. Okay? When you have a log, the base can't be a negative, and the argument can't be a negative. Okay? Neither one. Okay, and the range of the log function, that is negative infinity to infinity. Okay, if I go back and look at the function in red, it does go down forever, and it does go up forever. It goes up extremely slow. It goes up just as slow as the exponential function is fast at going up. All right, so when we write down expressions or equations that have logs and exponents, we're going to have to convert between two forms. Okay. One type of form is called log form. That's something like that, or like that. Okay. Another form is called exponential form. Exponential form looks like that. Okay. So what we're going to do is practice converting between that form and that form. Okay, and there's a formula to do that. Okay, so again, for this formula, I said earlier that the base has to be greater than 0. Okay, no negatives there. And for this particular formula, the base will not be a 1. Okay? All right. So there's three things, and we've got to figure out where they go. Okay. On the log, you have a base. That's a. You have an argument. That's x. And then you have something on the other side by itself. Okay. The first thing I do when I'm trying to change from log to exponential is figure out where the base is going to go. Okay. Because when you have a log, okay, a is the base. And when you write it as an exponential, a is still the base. Okay? The base is always the number below the exponent. And the base on the log is the number that's below the log. So the thing that's a little lower than everything else, that's always your base. All right, and then the next thing, this is going to explain really what a log is. Okay. A logarithm is an exponent. Logarithms are always used to calculate an exponent. So when you type in log of something on the calculator and you hit enter, that number right there, 0.30, that's an exponent for something. Okay, and I'll explain what that something is in a second. Okay, so the logarithm always equals the exponent. Okay, so y is the exponent. So when you rewrite it as an exponential, put the y up higher. That's your exponent. And if you can figure out where the a and the y go, then you're only going to have one thing left, and you're only going to have one spot left. Okay? These are your three spots in exponential form. That's your base, that's your exponent, and if you figure out those two, there's only one spot left.
Now I get why when you took the log of, was it 10,000 or 100,000?
I might have done 100. I think I did 100,000.
Okay, now I understand why it's 5, because it was base 10.
Yeah.
And
Yeah.
10 times 10, 5 times is 100,000.
Right. Yep.
So yeah.
Yep. Logs with that are a power of 10 are very easy to do in your head because it's basically the number of zeros. So the log of 100 is 2. Log of 1,000 is 3. If you want me to do something other than that, I really need a calculator. Okay. All right. So does anyone have that formula? All right. So let's practice changing something from log to exponential. Well, first thing is if you change it to exponential, the word log is going to be gone. Okay. What's my base right now? 3. So I'm going to put 3 as my base. And I said earlier, logarithm always equals what kind of number? Exponent. A logarithm is an exponent. So I use the y, I use the 3. What's the only thing I haven't used? X. That's how you change that equation from a log to an exponential. Now, why would you do that? Well, if you knew y was 2, you could solve it by doing what we just did. If y was 2, I could do 3 to the second power and then get the answer for x. Since I don't know what x and y are, I can't solve this. I stop. That's all I can do. Okay. Let's try this one. Okay, this would be another one that if you knew y was a certain number, you could solve for x. Okay, but since we don't know x or y, we'll just rewrite it. Okay, what's my base? 5. And the logarithm always equals your exponent. And what's the only thing left? X. Okay, so again, that's just changing it from a log to something without a log. All right, and we can also do it the other way. Now we're going to change it to something with the word log. So the first thing you want to write down, if you're converting it to a log, is the word log. Now, what's going to be the base on my log?
Or 1.2.
1.2, because 1.2 is the base here.
And that equals 3, right? 3 would be where...
1.2 m equals 3.
Yeah, 3 would be on the other side of the equal sign.
Yeah, because the logarithm always equals your exponent. So look at your exponent. 3.
Log 1.2 m equals 3.
Yep, log base 1.2 of m. M is the, what did we call the thing you plug into the log? That's the argument. Yep. So that's converting back the other way. Yeah, let's try another one of those. So log. What's my base here?
E.
E. We'll talk about that in a second. Logarithm always equals your exponent. So what's my exponent?
B.
B. And what's my argument? 9. Now, that's okay, but you probably would see that in more abbreviated form. What can I...
Oh, isn't it ln?
Right, I can change this to ln. So this one is saying b equals the natural log of 9. And that's something you could type in on the calculator. If you wanted the decimal answer, you could just take the natural log of 9, and it's about 2.2.
And that's what B would be?
If they wanted a decimal.
Yeah.
Yep. Okay, any questions on that one? All right. I want to show that that's true. Log base 2 of 8 equals 3. So in order to show that's true, what's the only thing I know how to do with something that's written in log form?
You gotta switch it.
Switch it, right? Change it to the other form and see if that helps. If that doesn't help, well, that's all we know how to do. So that will help. So what's my base?
2.
2. And Logarithm always equals what kind of number?
Exponent.
So 3 is the exponent. And what haven't I used? 8. What's 2 to the third power? Yeah, so of course that's true. That's the reflexive property. Something is always equal to itself. Right, so we showed that that's true. Okay, logs where this number is a power of this number are very easy to do in your head. Okay, so like this is another one I could do in my head, because 25 is a power of 5. Now if you made that a 24, I couldn't do it. Okay.
Did you reduce before you did that, or?
No, that's how you got to do it. Yep. So what would be the answer to this problem?
5 equals 25. Wait, next.
Where would the x go? Exponent?
Yeah, equals 25.
So this is just asking you 5 to what power is 25? So in this case it would be 2.
Yeah.
Okay. So as long as those number 25 is a power of the base, you're okay. If it's not, we got to learn a way to do it on the calculator. All right. So actually this one's almost identical to what I just did. Okay, my base is 5. What's my exponent? X. And that's equal to what goes on the other side. Now, let me go back to the other problem for a second. The problem I did before this had that. Okay, and what did we get for x in this problem? 2. Now, here you don't want 5 to the x to equal 25. You want 1 over 25. So what kind of numbers do you put in the exponent
Negative.
to cause it to flip?
Negative.
A negative. Okay? So now in this case, x would equal negative 2. Okay. Anytime you want it to be 1 over, you want it to flip, just make the exponent a negative and figure out what the answer would be to get 25. 2. Right, and you can check that on the calculator. If you want to try 5 to the negative 2, you get 0.04, and then just hit math, convert to fraction, and it tells you it's 1/125, which is what you wanted. All right, so let's try to solve that one. Okay, any suggestions on what I should try to do?
Maybe convert that to a fraction.
Okay, you could convert it to a fraction.
I mean, I don't know if it'd make it easier.
We're going to end up typing it in on a calculator, so whether you have a fraction or not,
Yeah,
it won't help too much.
we'll switch it then.
Yeah, let's switch it to the other form. How would you rewrite it?
5 to equals 7.
Yeah, there's your answer. Now, if they want the decimal, now you can just type that in. 5 raised to the 1.5. It's about 11.18. Okay, so very, very easy just by changing it into exponential form to get that answer. Now, you don't have a way to check that. Because at this point, you don't know how to type a base 5 into the calculator. So just do your arithmetic carefully, and then you'll be okay. All right, how about this one? A little different. This time, instead of the variable being the argument, the variable is in the base. So what would that one look like if you change it to exponential form?
X squared equals 3.
Yep. And now the goal is still to get the x by itself, and we got to do it a little differently than the last problem.
Square root.
Square root. So take the square root. Square root. And now remember, there are always 2 answers, right, when you do a square root. But what did I say about the base?
It can't be negative.
It can't be negative. So you don't need the second answer. Okay, so x is just the square root of 3. Any question on that one? All right, so that was where the base was an argument, and then, I'm sorry, where the argument was a variable, and this one was where the base was the variable. So either type you can solve. All right, so now we're going to look at some special properties with logarithms. Okay, and for all these properties I'm going to show you, they apply when a is a positive number, not equal to 1. And these properties are more patterns to look at. It's not really going to be any arithmetic or algebra here. It's just, if you see a special pattern, the answer is very easy to get. Okay, and here's one of them. Right, so if you have something that fits this pattern, a raised to the log base a of x. Okay, that's exactly what I have, for example, 6a. 2 raised to the log base 2 of pi. So the key is that this number matches that number. If that happens, what basically ends up happening here is that whole first part cancels out. And the answer that you get is basically whatever the argument is in the exponent. Okay? And it's just a special pattern. So looking at 6a, what would that simplify to?
Pi equals x.
Yeah, the answer is 3.14. Or pi. Okay? So because those twos match, it's basically like this thing cancels out, and the only thing that's left is pi. Okay, just a special pattern. We'll look at why the next one works. I'm not going to do why this one works, because it's going to be the same reason why this one works. Okay, so we'll look at the reason behind this one. Okay, so B is another special pattern, but this time it's this number matching that number. Okay, and if those two numbers match, the answer is whatever the exponent is on your argument. Okay, so looking at rule 2 and seeing what cancels out, what would be the answer to 6b?
-4.
Yeah, it would just be -4. Okay, and you really have to know that pattern because we have no way to type this in. We don't know how to type in a base that's a 0.2. Okay, so you just have to know that pattern. Let's see why this one works. Okay. Looking at number 2, what is your base?
A.
So your base is a. What's your argument?
A. Or x.
A to the x is your argument. And here's the thing that's on the other side. So let's change that to exponential form. Okay, doing just what you said. So you said my base was a. Okay. And the logarithm always equals what kind of number?
Exponent.
So in this case, it's equal to what I circled in blue.
Oh, I see that.
And now what's the only thing that I didn't use?
A to the x.
What I circled in green, a to the x. So all that rule 2 is really saying is something equals itself. It's not written that way. It's written as a log. But that's the reason why rule 2 works. Something equals itself. That's always true. Okay, rule 3. Okay, that's another one that's a special pattern, and it says log base a of a always equals 1. So I didn't write an example, but if you wanted one, log base 7 of 7 would be 1. Log base 13 of 13 would be 1. What's my base in this one? A. What's my argument? My argument is also A. And what's my, what's on the other side? 1. Okay, so my base is A. Logarithm always equals what kind of number? That's my exponent. And then that's equal to, what haven't I used? The green A. Okay, so this rule is saying that if you raise anything to the first power, you get itself. Okay? It's just written as a log, not the way you've probably seen it back in Algebra 1. So anything to the first power is itself. Okay, and the last rule, I'm just going to show you. I'm not going to go through the reason why, but if you do exactly what I did above, you could figure out why this one's true. This says log base a of 1 is always 0. So if you take the log of 1, it doesn't matter what the base is. The answer is always 0. So an example of rule 4, log base 12 of 1. What would that be? 0. That's the answer. Okay. Any questions on that? Okay. Just some special patterns to look for, and the reasons why they work. Really, it's not overly complicated. All right. So the last thing we're going to do with logs is learn some properties to combine them and split them. Okay. So sometimes you'll have a problem where you have a log and everything is grouped together, and they ask you to separate it out. Or you might have a problem with a log where it's already separated out, and they want you to put it together. Okay, so we're just going to learn the rules for doing that. Okay, so the first rule applies if you have a product, okay, inside the log. If you have a product, you can split it apart into a sum. So product splits apart as a sum of 2 logs. Notice the base on when you split it, base A, base A. The original was base A. The base doesn't change. That stays the same. The first argument is my first factor, and then my second argument was my second factor. And if I had a third argument, I could do plus, and I could do another one. So I'm just showing it to you for 2. But you could, if you had m times n times k, you could put plus log k on the end. Okay, so you can split it up as many times as you want. And there's an example with numbers. Okay, so this one I'll show you on the calculator. I'll type in log of 4 times 5, and I can do this for any base. But if I want to show you on the calculator, what's one base I can do quickly on the calculator? E or 10. I could do it for either one. Okay, I'll do it for base 10. So I'll type log of 4 times 5. So log 4 times 5, and I get that. Now let me type it as log 4 plus log 5. Log 4 plus log 5, and I get the same thing. Now what's 4 times 5? 20. So can anybody think of a different way you can break up the number 20?
10 and 2.
Yeah. If you did log 10 plus log 2, you get the same thing. Any two numbers that multiply to give you 20, you could split it up as addition. You could do 40 and 1/2. Okay, that would work as well. Okay, so that's the rule for when you have multiplication. Now, what do you think is going to happen with division? Yeah, it's going to split as subtraction. Yeah, very good. Now, with addition, the order is important. Okay, because when you add two things, it doesn't matter how you do it. Like if you do 2 plus 5 or 5 plus 2. But with subtraction, it does. So make sure when you split it, it's log of the top minus log of the bottom. Which kind of makes sense. You know, the top is first, so put the top first, and the bottom is second. So put the bottom second. Okay, and that's the same numbers I used last time. I'm just showing it to you with specific numbers. Okay, I'm not going to type this in, but if you wanted, you could check it, and it will work. Okay, and the third rule is really a special case of rule 1. Okay, I'm going to show you an example and see if we can figure out rule 3 together. Okay, does everyone have rule 2? All right. let's do log of x cubed. What does x cubed mean? Like, if, let's say somebody doesn't understand exponents.
Times x.
It means x times x times x. Now, earlier I showed you in rule 1, if you have multiplication, how does multiplication split apart? As addition. How many things am I multiplying? 3. So it's going to split as 1, 2, 3. 3 things. First log, second log, third log. Does the base change?
No.
No. Whatever the base was on the original, which is 10, because it's not written, but this works for any base. We're going to keep base 10 all the way through. Now, each argument, we just look up above at the things we multiplied. So what was my first argument? So x, and the second one, and the third one. So now I have a log x plus a log x plus another log x. So how many of those do I have?
3.
I have 3 of the log x's. So does anyone see what you could have just done with the original problem to get that final answer?
Put the exponent in front.
Yeah, all you have to do is take the exponent and move it to the front. That's the third rule. Okay. And the reason why it works, I just showed you. All right, so rule 3 says if you have an exponent, you can take the exponent and put it in front. And you don't have to go through all the steps explaining why. Okay, I showed you the why. Now we'll just put it in front. Now there is a time you can have a hidden exponent. There's an exponent in that problem, but it's hidden. And we talked about that on Monday. Does anybody remember what the hidden exponent is?
1/2.
Yes, it's a 1/2. And the reason you have to know it's hidden is because now that you change it to an exponent, you can use rule 3 and put it in front. Okay, so anytime you have a problem, I don't want to see a square root as part of the final answer. You always have to change it to a 1/2 exponent, and then you can use rule 3. Okay, so just remember that from Monday. All right, so what we'll do is we'll just practice some problems where we take logs and split them apart, and then we'll practice putting some back together. All right, so look at that argument and decide whether that's going to split as a sum or difference. Yep, it's going to be a sum because these are multiplied. So you're going to have log,
Log 4.
and what's the base?
4.
4 on each,
And then 3 and x.
and then 3 and x. Okay, and they get a little more complicated, but that's just using rule 1. Okay, any questions on that? So they said separate it into multiple logarithms, which I did, and they also said express powers as factors. Okay, that's going to come up in the second one. What that means when they say write powers as factors, that means take any exponents and put them in front. Don't leave exponents in the final answer. Okay, so use rule 3. All right, so how is this one going to split? As a sum or difference? Sum. Overall, it's this times that. Those are the two things you're multiplying. So we're going to have a log,
Base is 2.
and the base is 2.
It would be 5
5 is my first argument.
plus 3 log of r.
Right. The second argument would be an r cubed. But then the directions say to take that 3 and put it in front. So if you want to do both in the same step, that's fine. Okay. Any questions on that one?
I like this stuff.
Okay. How about, all right, a little different.
There's a difference.
Anyone think they can tell me the the whole answer there. Just keep in mind now it's a quotient, so it is going to split as a difference.
Log 9 minus x.
Log
Base 9.
base 9
Yeah, that's right.
of what?
X.
Of x.
Oh, minus log base 9.
Log base 9 of 2. Right, and as I said, it works the same whether you're using any base, so we can do ln. It's just when we split it, we're not going to write log, we're going to write ln's instead. Don't write log base e. Okay, use the abbreviation ln. Right. Anyone think they know what that one would be? Bria?
3ln y minus ln e.
Yeah. So it would be minus because we have division. And then the 3 goes in front of the ln y. And then the bottom was just an 8. Okay. Any questions on that one? All right. So now I think what I'll do is I'm going to go to the hardest one, which has everything. It has every rule in it at the same time. But as long as you follow all the rules, it's really not too bad. And then after this one,
There's a 1/2.
we'll try combining. Yep, we got to remember that there's going to be a 1/2, and that's in there somewhere. All right, so inside that parentheses, the first thing I like to do is deal with the fraction. Okay, so how does that fraction split?
Someone else can do this one.
Yeah, tell me just how you split up a fraction. What operation? Subtraction. So I'm just going to start by writing log of the top minus log of the bottom. Okay, and that's going to separate it into some simpler problems. So there's log of the top minus log of the bottom. And type everything that you have in the bottom. X cubed times, actually, you know what? Just put parentheses. All right, so now we've separated into at least a little bit simpler. Now, what can I do with this first part?
You can
Multiply it by 1/2. Put the 1/2 in front.
Right, you can do two things at once if you want, right? This really means this, right? You can change x squared plus 1 to a 1/2 power, and you could just do that one step and then rewrite the whole thing. Or if you want to do both at once, rewrite it and put the 1/2 in front. And that's pretty much all you can do for the first one. We don't have a rule for splitting it up when there's a sum. We only have a rule for splitting it up when it's multiplication, which we have, or if it's division, which we already did. All right? Now that second log, okay, I've got multiplication in there. So how is that one going to split up?
Log a x. Log a of x. Wait, 3 log a.
Let's do it in 2 steps, just so we don't do.
Alright, log a x of x to the 3rd.
Yep. Plus, because it's multiplication, that splits as plus.
Log a
Log
x plus 1 to the 4th.
x plus 1 to the 4th. Now, James had started
And then, yeah.
doing something that I'm just going to rewrite it, but you could do it in the same step. What's the last thing you have to do there?
Just move the exponents.
Yeah, copy that down, but just put the exponents in front.
Wow, that was long.
Okay, and then put 3 log base a x plus 4 log base a x plus 1. Okay, and that's pretty much as hard as it can get. So if you get that one, then there's nothing any harder than that. You do have to keep these brackets here, right? Because when you're subtracting this entire thing. So if you split that up into multiple pieces, you have to subtract each piece. That's why I left brackets around the whole thing. Right? And that's our final answer. Most problems, when you split them, they don't have that much, but that's one that's got everything. All right, so the last thing we'll look at is I'm going to give you one that's already split, and I just want you to try to recombine it. So to recombine it, you have to do everything just in reverse. So what would be the first thing you would do here?
Move the exponent, or move that back.
Yeah, put the 4 back as an exponent. And if you wanted, I mean, you can do this out. 3 to the 4th power. You could just type it in on your calculator.
Log A, or log base A, 7 times 4.
Yeah.
Or
So
3 to the 4th is.
because this is plus, okay, when James recombined it, remember addition must have originally been multiplication. And that calculation we can do out, which is 567. And the way I did that in my head is I just did 3 to the 4th is 81. And then I just tried to do 81 times 7 in my head. So it's 567. But you can just type that in if you need to.
So, would you take first part as the answer, or would you want us to do it out?
Nope, always do it out.
Okay.
Okay, always, you can use your calculator, so, yep. So any question on recombining that one? Okay, and this will be our last one. I need to change because this won't quite work. Make that 79.
All right, I'm not doing this one.
I love it.
Someone else do it. I got it.
Does anybody see something you could do right away there that's not even, it's not even logarithm rules?
Is it 3/4?
Yeah, 3 to the 4th, how much is that?
That's
81. And what's 81 minus 71?
10.
10. So, might as well simplify that.
Move the 2/3.
Yeah.
Wouldn't that be
Where would the 2/3 go?
an exponent?
Oh,
On what number?
8.
All right, and I'll show you how you do that. One way, just type it in on your calculator. Or it's not really that hard to do in your head. Okay, what I do is kind of block the denominator and look at, I have 8 to the 2nd power, which is how much? 64. And divide by 3 means a cube root. So what times what times what is 64? 4. Okay, so we just did 8 squared is 64. Cube root of 64 is 4. If that was a divide by 5, it would be a 5th root, and the answer wouldn't come out nice. But this one does come out nice. Okay, and now you have a subtraction, so when you recombine it,
ln 4 divided by 4 over 10.
right, subtraction must have been division.
Now
And
we
if,
can reduce that.
yep, if you can reduce it, just reduce it to, what did you say, John? 2 over 5. Okay, and it said express it as a logarithm. So they do not want me to type that in and get a decimal. Okay, so that's the basics that we're going to do with logarithms. We can review as much as we need to tomorrow because we're not going to do anything new. So if you want to come for extra help, you can. But we do have 40 minutes tomorrow. And all we're doing tomorrow is reviewing. So you can ask me any questions then as well. Okay, so the homework, it's on 292. Okay, it's 1 through 6, 13 to 16. And then it kind of jumps around a little bit. 21 to 23, 25 to 27, and 29 to 32. Okay, so we'll look at that tomorrow. We'll review for the entire class, and then we'll have our test on 4.4 5.1 and what we did today on Friday.